want to thank all the people who are attending this discussion. Who are the actual teachers who are hoping to benefit from this. And let me say right away, I want to make it quite interactive. So the first, I think, rule I should make is that you can interrupt at any time. Just unmute yourself and interrupt, because it is not a lecture by me as such.
Yeah.
The lecture actually is given by Feynman, and it's already given long ago.
Yeah.
So now we have it in print, and we are going to go through this chapter 15, which is and 16, both are on special theory of relativity. So I'll just speak for 5 minutes, and after that we'll start to identify what we want to discuss. So the point I want to make is, Feynman was, of course, a brilliant researcher, and he brought his research way of thinking into his teaching. Now, actually, because of this, Feynman lectures are not the best way always to study a subject from the beginning. I mean, they are not organized in a linear way that this step, this step, this step. They are actually, that makes them more difficult. And there are other books which are more simplified with more kind of linear exposition. I hope you understand what I mean by linear, that every step follows from the previous step. Feynman's way of thinking was little to go back and forth, and you'll see it already in chapter 15. He starts with something, but then he goes back to in 15.1, he starts by talking about mass, but he doesn't justify this formula 15.1 until much later. Then he talks about Lorentz transformation, but he doesn't explain why Lorentz thought of this transformation. And then in 15.3, he talks about this Michelson-Morley experiment, and now we can understand what he meant about why Lorentz thought of his formula. So I would like to help you a little by rearranging the order of the ideas so that we can follow them a bit logically. And for me, 15.3 is the starting point. By the way, that was also the starting point for Einstein. So in this discussion, I would suggest that we first start with section 15-3, the Michelson-Morley experiment, and try to understand the result of that experiment, because everyone was trying at that time to understand that experiment. First Fitzgerald, I believe, then Lorentz, then Poincaré, and finally Einstein. And each of these people before, they had some idea which was correct, but in a way which they didn't really know why. And Einstein just came and gave the complete picture. Okay, sometimes we feel Einstein came out of the blue and explained something. Actually, Einstein knew very well what other people were thinking, and he found the most deep or the most complete way of thinking about it. So we'll go over all those. But my point is that the first step was the experiment, 15-3 Michelson-Morley experiment, and its result. If that result had been different, the whole story, the whole of history and whole of physics would be different. Okay, so that result was crucial. And Feynman has emphasized here in his notes that we cannot predict what that experiment was going to tell us until it was done. So it was very important to do it. Only because it was done, we could understand what it is saying and then try to make some theory based on that. So this was a very key observation that Feynman has made in these notes. Now, after understanding this experiment, we can go back to 15-2 and see a little bit what Lorentz was thinking and see the formulae for Lorentz transformations. Okay, and then, but without any derivation still, because 15.2 is not derived in Feynman's notes over here. The derivation comes only after we start thinking about physical situations, and that happens in 15-4 and 5. And in 15.5, he actually works out the Lorentz transformation for X. He doesn't ever work it out for T. There's a transformation for T also, but I will show you how that follows from this same reasoning. And then he goes into discussion of few physical consequences, and finally into dynamics. Here in the beginning, we are talking of kinematics, which is only the behavior of velocities and so on, without saying what particles are actually moving and how they are interacting. When we talk of interaction, that is dynamics. So this is the sketch that I have made for this kind of discussion. And if there is a question or a comment or anything right now, I would be happy to hear it. And I'll also be happy to hear any other questions which specifically people would like me to address in this discussion. Don't seem to be any questions or comments. I don't think that is good, because I feel you must have gone through the chapter 15, right? And you must have questions. If you don't have questions, then why am I here? There must be some questions. So I really need to know the questions so that I can address them. Please don't be frightened to open your mouth and ask. That's the way interactive session will work. Organizers, what do you think I should do? I don't have any hurry. I have till 12:30, but I must have interaction. Otherwise, I'm talking just to a computer. That is not comfortable for me. I don't know who are the human beings in this meeting and what they want to hear and why they are here. So somebody has to, preferably I would like if you can unmute and even unmute your video. I can see you, then I can hear what you are thinking. I'm not expecting some deep question, just some question about what is the aspect of this chapter 15 that you feel you want to know a little more about. What is the thing that interests you to know more? Organizers, you have any suggestion? Maybe I'm not hearing. Is there somebody is having trouble to unmute, or you can also type in chat probably?
Sir, anybody can unmute and speak, sir. Actually, it is enabled.
Okay. So then I see there are a lot of people attending, 24 attendees.
Yeah, there are 26 there in total.
Okay. But nobody wants to speak. That's not a good sign. This is not. I'm not here to lecture to you. If I was lecturing, it would be different. But this is not a lecture, no. This is an interaction.
Yeah, sir. I have one question, sir.
Please, yes.
So in a length contraction, I think sometimes when you in a moving object, but when you observe, the length will be contracted, or so why it is like illusion, or when you actually it is decreasing?
Yeah, thank you. That's a good question. And that is exactly the kind of question which I'm hoping to hear from others also. So the answer to that is that it is not an illusion, but it is a illustration that what I see from one frame of reference is different from the thing which you see from another frame of reference. So let me show you a very nice paradox and we can discuss it. Supposing, so from now on, I am going to always have one frame to be stationary in some coordinates and other frame to be moving with velocity u. Is that okay? So the stationary frame, I'm going to give a person's name. Sarah is in the stationary frame, S for stationary, and Mona is in the moving frame with velocity u. Okay, M for moving, S for stationary. I hope this is clear. Now notice that this system is difficult to distinguish from a different system where Mona is stationary and Sarah is moving the other way with velocity u. Can you see that these are similar? from the point of view of the stationary person in the first one,
Yeah.
they are just at rest. That person says, I'm at rest. And that person, Sarah, says that, look, Mona, I'm seeing you moving. One second, finding the highlighter. Oh, yeah. So Sarah is at rest, but she is saying that, Mona, I'm seeing you moving in this direction with velocity u. And Mona will say, no, I think I'm at rest and I'm seeing Sarah moving in the other direction with velocity u. Up to now, I think we both have no problem with that.
Yes.
Yeah. Now let's move on. So we are going in very small steps. That way we can understand things. Okay. Now, supposing both of them have got a meter stick, a ruler. So it is exactly 1 meter for them. Okay. 1 meter for her, 1 meter for her. Both of them have 1 meter. In fact, let's say that before doing any movement, they were both sitting in the same room and they compared their meter stick and said, look, yours and mine are the same. They are made in the same factory. They are exactly the same, no difference. We won't worry about very small errors. We'll assume that within our errors, they are the same. Now, the interesting thing is that after Mona starts to move with velocity u, if Sarah measures the length of Mona's ruler while it is moving past, she will see that it is shorter. Okay, so instead of giving this length as 1 meter, let me give a number capital L. Feynman also uses capital L for the length. Okay, so in this first experiment here, Sarah will, so S will see M's ruler of length L times square root of 1 minus u squared by c squared. We are going to derive these formulae. I'm now assuming length contraction formulae, and I'm talking only about the meaning because that was the question. What does it mean? That was the question. Okay. So Sarah will see that Mona's ruler has reduced by this much. You can see that square root of 1 minus u squared by c squared is a number which is less than 1. That is clear. So L times a number which is less than 1 is less than L. So this number is less than L. Now let's ask Mona what she is saying. Mona will say, well, I don't think I'm moving. I'm stationary. Sarah is moving the other way. And Mona will also see Sarah's ruler to have length L square root of 1 minus u squared by c squared. That means each person will see the other one's ruler is shorter. Now, it looks like there's a paradox, but we realize that there's no paradox because one is in one frame and one is in the other frame. If they want to meet and compare, then one of them has to come to rest. When that person comes to rest, then the rulers have the same length because u is 0. So this is an effect of the motion. But it is a completely symmetric effect. Each person sees the same result on the other person. Okay. Now, technically, you may argue that, well, actually, Sarah's velocity in this second picture, just 1 second, I need to find out how to get a thing which will, let's see. Yeah, good. So in this picture, Mona will see actually Sarah's velocity is minus u. We should call it minus u because it's in the opposite direction, right? But you'll notice that this factor doesn't care whether it is u or minus u because it depends on u squared. So the factor is the same from in this picture and in this picture. And this is the picture that Sarah will interpret. This is the picture that Mona will interpret. And in each of them, the answer they get is correct and consistent. It's not an illusion because they cannot do any measurement which will actually show that the other ruler is of length L. Any measurement they do of the other ruler will give the result L times this reduced length. And what we are going to do today is to try and argue why this formula should be correct. This just now I have just told you the formula, and if you see Feynman, he has also just told you the formula. Okay, but at some point he will have to derive it, and we'll follow him and derive it. And I'll also show you a little bit how Einstein derived it. That way, if we get it from more than one different way, then we can sort of believe it better.
Yeah. Thank you, sir. Yeah.
Thank you. Okay, any more questions? That was a good question from the organizer. Now I want a question from the participants. Please, I request you, in order to make this a good experience for all of us, that you must interact. And after all, if we were in a physical room, you would be interacting, right? I would stop and I would ask you what you think. So please try to make this video interaction also like that.
Good morning, sir.
Good morning.
Sunil, sir, this is Dr. Devrat Singh.
Yes, good morning, Dr. Singh.
Sir, yes, sir. Sir, I want to understand this Michelson-Morley experiment outcomes, because every development of relativity in modern physics is more or less based on the outcomes of this result. So, sir, actually, ether concept. There are a lot of discussion on whether ether concept is still valid. Many people are following that. So, on the basis of Michelson-Morley experiment, can we say that that was totally perfect experiment and there is no ether?
Thank you. That's an excellent question. And actually, this question, it really brings up the meaning of how we do physics and how we believe experiments. So one might think that Michelson and Morley did some experiment in late 19th century, and now we are still believing it 130 or 40 years later. Why? And the answer is no, we are not believing it. That experiment has been done repeatedly. It is even being done today. In every possible physics experiment, we use or we check, we verify that this result of Michelson and Morley is true. It is repeatedly verified, and it is verified to much higher order of precision. It could have been true at that time that for some reason Michelson-Morley didn't have the precision to get the correct answer, and correct answer is not zero for the velocity relative to the ether. But this experiment is done repeatedly. It's not that it was done once and we believe it. And actually, it is also not true that anyone believes in the ether. Now, there are some people who talk about it in a different context. But let's first understand what is the role of ether. So, ether is a medium supposed to be that fills all of space. Okay, and then propagation of light takes place by some kind of elastic motion in that medium. Now, there's an analogy because sound is like that. So let's look at sound.
Yes.
In case of sound, we have the same picture and we have air. And the sound propagates only because there is air. You know, there is a famous experiment. If I take all the air out of the chamber, sound will stop propagating. I can make a chamber, I can put some music on one side and try to hear it from the other side. And if I remove all the air inside the chamber, now suddenly no music is going through to the other side.
Yes.
That shows that the elastic expansion contraction of the air is communicating the sound, and people had only that example, so they thought ether is doing the same job for light. In fact, that is the definition of ether. It is whatever medium is making light propagate. is allowing light to propagate.
Yes, sir.
Now, the modern view, which started with this experiment, is that there's no ether and light does not need a medium to propagate. It can even propagate in vacuum, unlike sound.
Yes,
So
sir.
light and sound are not at all similar. Even though we see them as similar, for example, we see lightning, then we hear thunder. So we think that, well, both were produced at the same time. That is true. Both are traveling to us. That is true. But light is faster. That's also true. But there's a basic difference that if the atmosphere of the earth suddenly disappeared, you would still see lightning, but you won't hear any thunder.
Yes.
You won't be able to hear the sound of it, but you will definitely be able to see it. And one proof is that between the sun and the earth, as far as we know, there's empty space. Now we know that very well. There's no ether, there's no medium, and still sunlight reaches us.
Yes.
So you can see how this ether concept, it was very important. Either the ether is everywhere or it is nowhere. Okay.
Yes. Yes.
It could be everywhere. We could have said that, well, the whole universe is full of ether and nobody can remove ether. That's why we cannot block the sunlight by removing the medium through which it propagates, because removal of ether is not possible. That is somehow what people were thinking. So unlike air. But the more radical result is there isn't even any ether. Okay.
Yes, sir.
Now, thank you. That's a very helpful question. And based on that, I would like to pursue this experiment and its derivation. So let's remind ourselves, what is the derivation? What is the experiment? So the experiment, you will see, I hope you have your chapter 15 with you open.
Yes.
So
Yes.
figure 15-2. So there are some mirrors and all. We don't need to draw everything. We just need to draw the paths of the light. So this he has called E, and this is B, and this one is C. I'm just using the same notation as Feynman. And these are supposed to be the same distance L. This is L, this is also L. Don't worry about my drawing, it doesn't look the same, but supposed to be the same. And now all we do is we allow light to go like this and come back like this after being reflected from this mirror, And in the other one, we allow light. So here also we have a mirror at C. And we allow light to go like this and be reflected and come back from there. And the time, of course, if this equipment is completely stationary and if there is no ether, then the time should be exactly the same. Right? Because then the direction doesn't matter, traveling the same length and reflecting from a mirror and coming back. So transit time should be exactly the same. Now, supposing we are moving with respect to the ether, so that means the whole earth is moving at velocity u with respect to ether. This is suppose. Okay, we suppose this. Now we can do a calculation of what should happen. Okay, and suppose, let's say two things. One is this, and two, old physics is true. That means Newton's physics. That means without assuming any laws of special relativity, which came later. Okay, so we assume that Earth is moving and old physics is true. That is obviously what people assumed at that time. Both these assumptions were normal common sense assumptions at the end of 19th century. Now, if these two are true, then we can calculate transit time, and let's call it B to E to B and B to C to B. I hope it's clear. First one is this way and back. Second one is that way and back. And we can show that they are different. You'll find different answers. What are the answers? First, let me write the answers. So, and then I'll show you how we calculate them. B to E to B. The answer is 2L by C over 1 minus U squared by C squared. And B to C to B is 2L by C over square root 1 minus U squared over C squared. Both are very easy to derive with these assumptions. Remember, we can only derive something with some assumptions. These are the assumptions. Okay, so let's do this calculation and you see that we get different results. I'm postponing the calculation by 2 minutes. Now, these are different. And that's the important thing. Okay, but Michelson-Morley experiment finds that B to E to B and B to C to B are equal. This is the contradiction. It's a huge contradiction. Now, let's notice that this denominator in both these formulae, if U is small, it's very close to 1. Okay, so in that limit, they actually become equal if U is very small. Okay, and this is where experimental accuracy becomes important, because it means that if I can measure very accurately the difference between these two, then I will be able to detect the difference between 1 over 1 minus U squared over C squared and 1 over square root of 1 minus U squared over C squared. Obviously, for any number which is not equal to 1, that number and its square root are not equal. Okay, so there will be some difference in this formula. And the question is whether they could detect that difference. Now, they did it by interference between light beams. And the beautiful thing about interference is that it can detect any change of the size of the wavelength of the light beam, which is in angstroms. Okay, so if these two numbers differ even by angstroms, even though L is 1 meter and in this formula, supposing the difference between these two times is of the order of 1 angstrom in distance, then I'll find it. And they didn't find it. Okay, note one more interesting thing. They didn't even have to assume that these lengths are exactly equal. Okay, what they did was they did the experiment once like this, and then later they rotated the whole thing by 90 degrees so that C becomes E and E becomes C. Okay, and they simply asked that does anything change? So you see that even if these lengths are not exactly equal because of some experimental limitation in the lab, it doesn't matter, because in this case, I should get a discrepancy, and in the rotated case, I should get opposite discrepancy, because now remember, the motion of Earth is assumed to be in some direction. We don't even know what direction it is in principle, because we don't know where how it's moving through the ether. But whatever it is, by rotating the apparatus, the effect cancels out, because if B and E is along the movement of the Earth, then after rotation, B and C will be along the motion of the Earth. Okay, so in one case, one time will be longer than other time. In the rotated case, other time will be longer than the first time. And what you will see as you rotate it is a shift in those fringes. You'll actually see a shift, and they didn't see a shift. So it's very, very accurate, and we have to believe it. Okay. Now let me ask people, Feynman has given a derivation. Shall I repeat the derivation?
No, sir.
Okay, good. Because the derivation is very clear, 15.4 and 15.5 of his notes, and it's very easy for anyone to reproduce that. Let's notice something about his derivation, only just say some words. The main feature of the derivation is that if u is the velocity, let's just assume for the derivation that u, which is the velocity of the Earth respect to the ether, is in the same direction as this horizontal axis, okay, then the transit time in one way and the other way will be different, because in one case the velocity of light increases by u, and the other case it decreases by u. Okay, because it's the velocity of light, but the object is also moving. It's very much like the velocity of an aeroplane relative to the wind. If a plane is flying against the wind, then its speed with respect to the wind is greater. If it's flying along the wind, then its speed with respect to the wind is smaller. So it's the same effect. So these two are not symmetric, going and coming, and he calculates the time taken for each and he adds it. On the other hand, if you look at the upward going thing, then actually because of this velocity u, this thing is moving. So the light actually is going there, then it hits the mirror and comes there. Okay, now there's a diagonal effect. Basically, it's no longer moving at right angles, but in order to hit the mirror, it's moving at a certain angle with respect to the vertical. And this will introduce some different distance that the light has to propagate. But in this direction, effectively, the speed of the light is not changing because it's perpendicular to the motion. Okay, but the actual length that it travels is changing. And that is what gives rise to 15.5. That effect comes from the change of length of transit of the light. So there are different effects. 15.4 comes from the difference. The length is the same in both directions, obviously, and it is L. But the speed of light is different going and coming. That is 15.4, and in 15.5, the length is of the rod is still L, but the light doesn't travel along that. The light doesn't travel straight like this. It travels at an angle like this and back at an angle. And obviously this line is longer than this line by a factor. And that is the denominator in 15.5. So I've given you a quick way to remember the two formulae. So now we assume that they have been derived. And now we think, let us put ourselves in the shoes of Mr. Fitzgerald or Lorentz. Okay, this calculation anyone could do even before relativity. This calculation assumes old physics. Okay, now they have this calculation showing two different answers. Sorry. They have this calculation showing two different answers. And they are staring at it and saying, look, the experimenters have found the same answer. Now, how can we adjust with that reality? So there are two options. Either the experiment is wrong or this calculation is wrong, or some assumption in this calculation is wrong. And obviously, a lot of people thought the experiment is wrong because Newton's laws are correct for so many centuries. How they are going to become wrong suddenly overnight because some people did one experiment. Okay, so they looked for all ways that the experiment is wrong, but nobody could find it to be wrong. Okay, then theory is wrong. So what assumption could be wrong? Now, what is the difference between these two factors, this one and this one? It is that here there's a square root and here there's no square root. So supposing here the length changes by a contraction, that L goes to L times root 1 minus u squared by c squared for some reason which we don't know, then that square root factor will cancel part of this denominator and leave behind this square root factor, and the two will become equal. So the guess, and it's only a guess, is that for some reason this length is not L but L square root of 1 minus u squared by c squared. Guess. At the same time, the guess is that this L, this one, is still L. It is a length perpendicular to direction of motion that is not supposed to change. Okay. Now, the guess is very wild that this is happening. And the guess is saying anytime there is a motion, the length will contract by this much. Okay. The point is that if I make that guess and I put it in this formula, this L came from a rod which was parallel to the direction of motion. So it should be replaced. So this one should be replaced by L square root 1 minus U squared by C squared. But this should not be. This is still L. Okay. And now you can see very clearly, I hope, and please stop me if you can't see it clearly, that this one and this one cancel to give me square root. And these become equal. So this is the basis of Lorenz's observation. Okay, Lorenz said, well, if lengths contract, then these two formulae become equal. He didn't say why lengths should contract, and he didn't answer questions like what was asked to me in the beginning today, which is that is it real or is it an illusion, or how is it possible that one person sees the other person's length contract and other person sees first person's length also contract? There's some paradox. Is there a paradox? All of those questions Lorenz did not address. He only got the formula. Okay, and from this formula, he was able to derive also what is the way that X and T should change under a change of frame. But the deep understanding of what is going on, that did not come to him. That is due to Einstein. Okay, so this is the Michelson-Morley experiment. And as you see in Feynman 15.7, he has pointed out that supposing this distance L parallel is shortened 15.6. This is Lorentz. Then, in fact, 15.7 is an answer which agrees with 15.5, and then there's no paradox and everything works. And the question is why? Okay. Now let's go to the thing that Einstein did. Now here I have two options. I can either show you how Einstein did it, or I can show you how Feynman does it. There are two different ways. Okay. Feynman's way, maybe you have already gone through it. It is given in section 15-5. He has Joe and Mo, and he explains how the observations of one person of the other is like this. Here we assume length contraction, and we get directly x prime equals x minus ut upon square root of 1 minus u squared over c squared. Okay, but this is assuming length contraction. So, but we haven't derived that yet. Okay, Einstein did it in a way which I find very beautiful, and it's a little more algebraic, more mathematical, not so pictorial, but it's very easy in my opinion. Okay, and Einstein said the following. The speed of light c in vacuum is the same in all inertial frames of reference. What is inertial? Moving with respect to each other at constant velocity. Okay, no acceleration is allowed. He also said that the laws of physics are the same in all frames. So these are his two main postulates. One is this, and two is that laws of physics have the same form in all inertial frames. Now, out of all this, all the consequences of these statements, there's one which is really simple, which is the following. So let's assume that light travels from a point, some origin in space, which I'll denote by 0, 0, 0, to another point x, y, z. Okay. So what is the distance? Distance traveled is square root of x squared plus y squared plus z squared. What is the speed of the light? It is c. So what is the time it takes to do this? It is t equals square root of x squared plus y squared plus z squared upon c. You agree with me? Okay. So from this, we take c to the other side and square both sides. We get c squared t squared minus x squared minus y squared minus z squared equals 0. Now, Einstein says in all frames, the speed of light is the same. So in a different coordinate system or a different frame, the different frame can be a different coordinate system for space. It can also be a different coordinate system combining time and space by moving. That is what happens when I move. Okay, because my space coordinate now becomes time dependent. As I move, my location keeps changing. Okay, so in a different frame where the coordinates are t prime, x prime, y prime, z prime, the same equation must hold. But c must be the same in both equations. Both of these equations are true. As long as one frame is moving at velocity u with respect to the other. Okay. Now, let's try to analyze this. So to simplify our lives, let's assume that y and z don't do anything. So we just remove them from this. We assume that the motion is all along x direction. Okay, it's just to simplify the actual calculation. And the resulting transformations we find will be that y prime equals y and z prime equals z. Okay, so that confirms that I can cancel them and I can compare the rest. So the statement is that c squared t squared minus x squared is unchanged by a linear transformation of the form t prime equals, let's say, so let me start with x. Please stop me anytime if there's anything confusing. X prime equals, let's say, ax plus b t, and t prime is cx plus d t. This is the most general linear transformation which relates the two frames x and t with x prime and t prime, where a, b and c and d are something I don't know. Okay, but now my requirement, oh, c is not a good thing. I should have not used c because it is the speed of light. So what shall I do? Let me make them capital. Please don't mix up the capital C with small c. Okay, now the statement is that c squared t prime squared. Okay, so this is not a good way to write it actually. Let me also write it a little bit better by putting the speed of light c here everywhere wherever time comes. Can you guess why I'm doing that? So I've just chosen my coordinates instead of x and t. I chose x and ct. Can someone tell me the reason why x and ct is a better choice of coordinates than x and t?
Sir, probably to keep the dimension same
Very
of
good.
x and.
Thank you so much. That's exactly right. Because ct has dimensions of length. So now a, b, c, and d are just pure numbers. They can't have any dimension. Okay? Then both these equations are dimensionally consistent. And luckily, the ct is also what occurs in this equation. So now we say that, well, A, B, C, and D are such that c squared t prime squared minus x prime squared is the same as c squared t squared minus x squared. We impose that condition and we try to find out how it fixes A, B, C, and D. Okay, so I can simply plug this in. Let's plug it into the left side. So I use this equation over here and I use this equation over here. Okay, so I get Cx plus D Ct whole squared. Okay, minus Ax plus B Ct whole squared equals c squared t squared minus x squared. Okay, now I can expand out these brackets and I get capital C squared x squared plus capital D squared ct squared. It's a bit algebraic, but the calculation is very simple. Okay, this is expanding the first bracket, this one. And now I'll expand the second bracket with a minus sign. I get minus a squared x squared minus b squared ct squared minus 2ab xct. Okay, now let's look at this result. It has two terms in x squared which have to add up to this. It has two terms in ct squared which have to add up to this. And it has these two terms which are cross terms x times ct, but they are not there in the final answer, so they must cancel. So we get three conditions on these numbers a, b, c, d, and the conditions are that ab equals cd and c squared plus d squared is equal to, sorry, excuse me. C squared minus, oh, this C is looking very small. C squared minus A squared should be minus 1. And D squared minus B squared should be 1. So if D squared minus B squared is 1, then these two terms nicely combine into this. And if C squared minus A squared is minus 1, then these two terms nicely combine into this. And we have implemented the fact that this is true, this equation. We are just working with one equation and we are assuming a linear transformation, which is what happens in an inertial frame. The coordinates in one frame and other frame will be linearly related. If I accelerate, then the relation may not be linear and then everything in my derivation will break down, but I'm assuming inertial frames. So these are the three conditions. Okay, now I have to find four numbers such that they satisfy these three relations. Okay, so three conditions on four numbers means there's only one independent number. And now I have to be a little bit clever to guess how to describe these four numbers in terms of one number such that they satisfy this set of three conditions. They're just algebraic conditions. Now the trick here is to realize that if this minus was a plus, sorry? Somebody talking to me?
No, sir. I think
somebody has forgotten to unmute their mic. You know, after 3 years of COVID, we should, or 2 years of COVID, we should be used to this muting requirement. Anyway, okay, so good. So the trick here is, supposing this was plus and supposing all these minuses were plus. You may say it's very silly. Why am I saying suppose minus was plus? Minus is minus. I can't make it plus. But actually, it's a good intuition. What kind of numbers satisfy that d squared plus b squared is 1? You know this from geometry. Okay, just one of them is cos theta, the other one is sin theta. Then cos squared theta plus sin squared theta is 1. It's very simple. Okay, and it shows the invariance of a length under rotations. But these are not rotations. What we are doing here are more general transformations called Lorentz transformations, which is an inertial change of coordinates between one frame and another. But there's no plus sign, it's a minus sign. So are there some nice functions such that they obey that the difference between those is always 1? And there is a very nice function. It's called the hyperbolic cos or cosh. Okay, so supposing we say that d is equal to cosh of some alpha and b is equal to sine hyperbolic of alpha, then there's a result that cosh squared of alpha minus sine hyperbolic squared of alpha is always equal to 1 for all alpha. Okay, now maybe some of you are not familiar with this cosh and sine hyperbolic functions. If so, I can tell you what the function is very easily, and you can prove this result. Cosh of alpha is just the exponential of alpha plus exponential of minus alpha over 2. And sinh, sometimes people call it, is the same thing with a minus sign. If you actually check this now and take square of the first one, subtract square of the second one, you will get 1. Okay, is this familiar, unfamiliar? I'm just wondering. I don't have much feedback. People know about, yeah?
Yes, sir. Yes, sir.
Now, the beautiful thing is that I'm just guessing here, but it's easy to prove rigorously. If I just choose D to be cosh and B to be sinh, then this equation is satisfied. I still didn't manage to make the other two equations satisfied. Okay, but what I can do is in this equation, I'll choose A to be cosh of some other number beta and C, capital C, to be sinh of that number beta. Okay, so now I have satisfied this also. Both are satisfied. Finally, I look at AB equals CD. Okay, so notice that AB is this times this, cosh of beta and sinh of alpha, while CD is this times this, which is cosh of alpha sinh of beta. These will be equal only if alpha and beta are the same. That's the last step that makes this equation also true. Okay, so now we have found that x prime, going back to our original linear transformation, it's ax plus bct, this one. Okay, so we decided that A is cosh, so it is cosh alpha times x plus sinh alpha times ct, and T prime is sinh alpha times x plus cosh alpha times ct. So actually we have got the linear transformation between the most general one, which preserves the speed of light. This is the mathematical solution to the question, what linear transformation between two frames xt and x prime t prime preserves the speed of light? Preserves because in both these equations, the speed of light is the same. You could try to apply these to some other particle, but then this speed and this speed will not be the same. And then we don't have this result. It's only for light where, as per following Einstein, we are assuming that speed of light is constant in all frames. Then we get this. Now, that much was some basic mathematics, but it doesn't tell us physically what it is. What is alpha? Only thing we can say at this stage is that, well, alpha is something related to the speed u of one frame relative to the other frame. That's also one parameter. Alpha is one parameter. They should be related and they must be related. Now it's up to us to find the relation. Now to find the relation, we notice that if x prime is 0, then we have that so x upon ct is equal to, so let's just assume x prime is 0, then this side of the equation is 0. Okay, so we take this to both sides, to the other side. Let's do all the steps. So cosh alpha times x is equal to minus sinh alpha times ct. Okay, therefore x over Ct is equal to minus tan hyperbolic alpha. Okay, but if x prime is 0, then x relative to Ct is moving at the speed of the frame. So this ratio is just u by c. X upon t is u. Okay, because if I ask the question, I fix x prime to be 0. So Mona fixes that her origin is at 0. Okay, now what is the difference between her position in Saira's frame, in the stationary frame, after a time t? So that position is x and the time is t. But in that time, Mona has moved with a velocity u. Okay, so x upon t is u. So that was a clever step, that if we fix x prime equals 0, then the ratio x by t is nothing but the speed of the frame u. And so we get our relation which we have been looking for between u and tan hyperbolic of alpha. It is u by c is minus tan hyperbolic of alpha. And from this, I get that cos of alpha. So once I have tan, I can get cos and sinh. Just like from tan function, I can always find out sine and cos. Okay, how do I do it? From tan function, I can get the angle, and from the angle, I can find sine and cos. Or I can find sine and cos directly in terms of tan. So there's a simple formula. So it turns out that cos is 1 over root 1 minus tan hyperbolic squared of alpha. This is just a relation between cos hyperbolic and tan hyperbolic. You can easily prove this. Okay, if you want, I can prove it here also. You can ask me. And therefore, this must be 1 over square root of 1 minus u squared over c squared. Aha, we are getting the function that we want. And what can we say about sine hyperbolic? Well, that is equal to u by c upon, actually minus u by c upon square root of 1 minus u squared by c squared. If you look at these two expressions, then cos squared minus sin squared is exactly 1. Just take the right side, do the calculation, you get 1. So with this, and realizing that cos of alpha is the same as d and also a, then we find that going back to this equation, here we must put cos and here we must put cos. And here we must put sinh and here we must put sinh. That's all. So we do that. And finally, we get that x prime is equal to x minus ut upon. OK, so now actually, we have to be a bit careful. It is minus u by c into ct upon square root of 1 minus u squared by c squared, while t prime is equal to t minus u by, so ct prime is ct minus u by cx over square root of 1 minus u squared over c squared. I just plugged in whatever I found. And now it's just a matter of moving the c factors around to get a convenient form. So in this one, it's very easy. This c just cancels this and I get x minus ut upon square root. And in the second one, I'll divide by c throughout on both sides of the equation because I want. Please.
You didn't get that CD prime.
Sorry, there's some echo. Sorry. What was the question?
Yes. So CT prime, I didn't get it. How it comes? Can you go back to that?
Sure, I'll do that. 1 second. I'll just try to stop this call. Yeah. Yeah. So you wanted to know how I got this equation for CT prime, this one here?
Yes, sir.
Okay, good. So let's go back and remember what is the original thing we assumed. We assumed that CT prime is Cx plus d times Ct. So capital C and capital D we need to find. And my claim is that this is nothing but sine hyperbolic and cos hyperbolic of that parameter alpha. Okay, let's check that. C is sine hyperbolic and D is cos hyperbolic, and beta is equal to alpha. So C is equal to sine hyperbolic of alpha and D is cos hyperbolic of alpha. I put that in here and I got, then I put in the fact that the sine hyperbolic of alpha is this thing and cos hyperbolic is this thing. So it's just all stepwise, just keep substituting. Okay, and that's how I get this.
Okay, sir.
So another way to say it is that 1 over this square root, this much, so 1 over this is nothing but sine hyperbolic. So I can write it here as sine hyperbolic alpha. Let's write it with the proper pen. Times Ct plus, sorry, I meant other way around. Try keep mixing them up. Cos is the one with 1 upstairs. You see from here, sine is the one with minus u by c upstairs. Both have the same denominator. So this is the same as cos alpha plus sine hyperbolic alpha x. Now here I plugged in the values of cos and sinh and I got this. So Ct is Ct, x is x, and both of them have the common denominator, and cos has a numerator 1 and sinh has numerator minus u by c. Is that clear? Is it okay?
Yes, sir.
Okay. Now I just divide the second equation through by c and I get t minus u by c squared x over square root. And now you recognize we have exactly derived equations 15.3. Word for word. Everything is exactly the same. Only thing y prime is y, z prime is z. We didn't go into it because we didn't need it, because our motion was along x. You can always write these Lorentz transformations for more general motion along any direction, or better, you can always rotate your coordinates so that whatever is the motion direction, it is rotated to become x. Then you get this form and it's much easier to use. But I want to emphasize this is a derivation of that formula. While Feynman doesn't offer a derivation in 15-2, he just writes the formula. And I'll suggest to everyone, please make your mental note that when you are seeing a derivation and when you are seeing a statement, very important when reading anything. So in Feynman, when reading it, you in 15-2, you should say, he is saying something, he has not derived it here. Let's hope that he derives it later. And then eventually, after discussing a lot of physics, in 15-5, he says, let us try to return to the Lorentz transformation and try to get a better understanding. And he gets this one. But he doesn't do it the way I showed you. The way I showed you is the way Einstein did it. Okay, it's more algebraic, honestly. Feynman's way is a little bit more physics oriented, basically, but assuming length contraction. So in some way, so here we didn't assume length contraction at all. Length contraction will follow from our formulae. What we assumed instead was that speed of light is the same in all frames and the laws of physics are the same in all frames. Even that second thing we didn't discuss because we haven't talked of any law of physics. We're just deriving the transformation of coordinates. So we only need the speed of light to be the same in all frames.
Sir, good morning. I have a question.
Yes, please.
Yes, sir. So Einstein assumed that speed of light is constant. So
Yes.
was there any physical basis of that assumption in Einstein's time or something
Well,
like
that was the Michelson-Morley experiment. That was the basis for his assumption. But it was a bit stronger than that. Or Michelson-Morley said that whatever change takes place in speed of light due to motion of the Earth against the ether, that change we cannot find. So there's no change. Now, from there to go to a assumption that all of physics, whenever you change a frame in an inertial way, in every possible system and experiment, it will always hold that speed of light is the same. That's an extra assumption, and that was Einstein's brilliance. Lorentz did not, I think, make that assumption. Poincaré did not make that assumption. Fitzgerald did not make that assumption. Only Einstein thought of that. And it was like what you might call a unifying idea. It explained not only that experiment, but predicted the result of a whole series of experiments which have been done repeatedly, which are done every single day. Whenever we do any particle physics experiment at the Large Hadron Collider, for example, at CERN or anywhere, or even in a lab, whenever light beams travel time is measured or fast moving particles are measured, we always find that the speed of light in vacuum never changes whatever we do as long as our frame is inertial. So it was an assumption, but it was very clearly motivated by Michelson-Morley experiment. Without that experiment, he couldn't have made the assumption.
Okay.
And in
Sir,
a way, Einstein's real greatness was, he said, look, the experiment is telling us something, let us believe it. People have spent 20 years trying to prove the experiment wrong. Let me believe the experiment and see what follows from that.
and sir, I have one more question. In the last part, we were talking about ether.
Yes.
So ether is something we know that the definition was like something that it is an all-pervading medium,
Yes.
and everywhere you will find something like that. So if we look at the modern physics, how much it has developed, we know that whenever any particle travels, whether it is light or any massive particle, it essentially follows a geodesic.
Correct.
Now, the geodesic, which is a function of space-time. Now we know that the space-time from QFT, we know that okay, this space-time is filled with some vacuum energy, and whose fluctuations give you the particles or things. Now, can we make an assumption that this vacuum energy is actually behaving something like an ether, or it might be behaving like an ether?
So that's a good question, but I think we have to be a bit clear about what we are trying to do here. So first thing is that there's no quantum theory in this discussion.
Yes, I was just a bit curious.
Sorry?
I was just a bit curious on
No,
listening
it's a
this.
good thing to be curious about. So once there is no quantum theory, we have to use classical physics, and what is special relativity is nothing but the corrected laws of classical physics, corrected from Newton by taking account of constancy of speed of light. Okay, that's one of the main points. Now, after understanding special relativity, we may say now we want to do quantum theory. How does special relativity work in quantum theory? That's actually a very difficult question to answer, and it is answered by quantum field theory, as you mentioned. Okay. Now, in quantum field theory, I simply don't have these kinds of equations because my dynamics in quantum field theory is governed by operators and quantum fields. Okay. Of course, the laws to change coordinates among frames are still whatever they are, which I've just derived for you. But the meaning of vacuum energy, 0 point energy, and all that comes in a context which is quantum. Okay. And it cannot be the medium that carries light or anything, because we can look at systems where the vacuum energy is completely negligible and yet light is able to propagate. Okay, vacuum energy is an extremely small quantity, and it effectively, we didn't know until 20 years ago whether the universe had vacuum energy or not. Okay, the so-called cosmological constant. On top of it, there's vacuum fluctuations, but none of those is really ether. Ether is a classical concept. So first we give up the concept of ether, and then we build our physics around the concept of special relativity, then general relativity, then quantum field theory, and whatever it comes from that, but it won't be ether. It will be something else. We'll find some quantum rules for propagation of light. They're different from classical rules. but they don't obey law of addition of velocities. Like you cannot add something to speed of light, even in quantum theory.
Yes, sir.
So
Yes,
in
sir.
that sense, these are very different domains. We are trying to do something very, very basic without even, I mean, while pretending that we don't even know quantum theory. And that's because in 1905, quantum theory was not known.
Yes.
So we are doing something which comes before understanding quantum theory.
Oh, thank you.
Okay. Now, one question which I was hoping somebody would ask me, but since you're not asking, I will tell you the answer. If you look at 15-5, the Lorentz contraction, you see that Feynman has derived it using measurement of distance in two different frames and comparing it. Okay. So Joe in the stationary system, that is our Saira, is measuring a distance to be x, while Mo, who is our Mona, in the moving system, has measured a distance to be x prime times the square root to make the length contract, and plus u times t, because in that time she has moved that distance. Okay, and since these two should be the same, we compare these two and we get that x prime is x minus ut upon square root. Now the question is, that's only one of the Lorentz transformations. Okay, that is this one. What about this one? Why didn't Feynman derive this one? He doesn't. Nowhere I think he derives it in his lectures. And this is why when we read somebody's lecture notes, we should notice that. First thing we should notice is Feynman doesn't derive it. Can I derive it, or can I ask someone to derive it for me? Even I didn't really remember because I'm not open Feynman lectures for a long time. So yesterday I was trying to figure out why he doesn't do it and what I can do to remedy it. And there's a very clever way to remedy it. So let's assume we only know this equation, x prime is equal to x minus ut upon square root. I hope you won't mind when I put square root like that. I won't write inside what is there. You know what is there. It's 1 minus u squared by c squared. Okay. Now, let us assume that okay, so now remember I started this lecture by mentioning that Saira and Mona are in a symmetrical situation, that one thinks she is at rest and other is moving, other thinks she is at rest and other is moving in the opposite direction. Okay, so from this x prime is the moving, this is Mona's coordinate, and this x and t, they are the and these x and t are the coordinates of Saira, who is stationary. Okay. Now, supposing I do the same calculation from the point of view of Saira, who is stationary, to find x as a function of x prime and t prime. What should I find? The only difference between the two people's perception is that while Saira sees Mona as moving with a velocity plus u, Mona will see Saira to be moving with a velocity minus u. Therefore, Mona should have x equals should have x equals x prime plus u t prime over square root. And square root is always the same. It doesn't depend on plus or minus u. I already told you that. You see that? Now, this relation is just obtained by symmetry from this. If this is true, the same derivation will tell me that the second thing is true. Do you agree with that? And notice that both relations contain x and t and x prime and t prime. So I can eliminate one of the variables between both of them. So let's eliminate x prime. So what I'll do is x prime, which is here, I'll plug in this amount right here. Okay, then I'll add ut prime divided by this is equal to x. Now I'll rearrange the equation so that I'm solving for t prime. And in fact, I get that t prime is equal to t minus u by c squared x upon square root 1 minus u squared by c squared. So I don't need to do a different discussion of how to derive the t prime Lorentz transformation. All I have to do is say that, look, whatever when Mona says that, well, my x prime is x minus ut over square root, Sarah will equally, with equal validity, will say that no, my x is x prime plus ut prime over square root. Both must be true. Okay, so if I derived one of the equations, I can derive the other equation in the same way. Only difference is that the direction of movement is reversed relative between them. And now I can eliminate x by inserting, as I said, this into here. By putting this whole thing in place of this x prime, I get some complicated thing, but now you see that it depends on x and t prime. So I can solve it for t prime. And when I solve it for t prime, this is the answer I get. So the second equation of the Lorentz transformation follows, and Feynman could have actually added one paragraph here just to say that, and his lecture notes would have been more complete. But then these notes were taken by his students. He may have not had much time, or he may have wanted his students to do it themselves as an exercise. Okay, so that much is done. What else should we talk about? I have to leave sharp at 12:30. I'm sorry about that, but that is still 12 more minutes. So I'm with you for 12 minutes, and I'm happy to address any other question you may have here. Yes,
Sir, I
Dr.
have yes, sir. I have the derivation that you just showed, that plugging in x value of x prime in something. Isn't it actually the rotation matrix that we were getting earlier in terms of ABCD?
Yes.
And rotated in an opposite direction, like if it is along plus theta.
Absolutely, it is that. You're exactly
It is.
right. In fact, sine hyperbolic is an odd function.
Yes, sir.
So
that will change.
Yeah, that will change, in fact, to minus itself. And actually, we have already seen here the relation between the sine hyperbolic. These are the rotation. They are not literally rotation. They are called, you can call them hyperbolic rotation, because they are rotation between space and time, not between space and space. But you can see that as u changes sign, this will change sign. Denominator doesn't change, and cosh doesn't change. Cosh is an even function.
Even function.
Yeah.
So it is parity invariant, so it will not change.
Yeah. So that means that alpha, that u changing sign is same as alpha changing sign.
Yes, sir.
Yeah. So in fact, we can also get that from this equation, which said that u by c is minus of tan alpha. So obviously, if u changes sign, tan hyperbolic is also an odd function, so alpha will change sign. And it's exactly the fact that one person sees the other frame moving with plus u, then second person sees the first frame moving with minus u. And the analogy with rotation is good, because if I sit fixed and somebody makes a rotation by theta, then that person, if they sit fixed on somebody else sits fixed on the apparatus, then they will see that I and the whole rest of the world is making a rotation by minus theta. Exactly the same idea. But I want to emphasize that from Einstein's derivation, which starts with this fundamental pair of equations, that c squared t squared minus x squared and c squared t prime squared minus x prime squared, these are equal. That derivation immediately gives you both the answers for x prime and for t prime. Okay, and Feynman's method, which is assuming length contraction, gives you the x equation. And from that, you have to do little extra work. This is here is the x equation. And then you have to do a little extra work. This is the x equation. You have to do a little extra work by introducing this one, and then eliminate x prime, and you get this. And since we were able to get this equation using length contraction, we can run that in reverse. We can use this equation to derive length contraction. Actually, it's very simple. You just have to put the right words to it. You have to imagine the right physical situation, and then you will get it.
Yes, sir. Thank you, sir.
Thank you. Other questions? More basic questions are fine. I think what I did was little bit mathematically bit intense. And maybe this is not what we want to teach our students on the first day, but certainly if we are going to some graduate level or something, or even final year of BSc, then we can certainly go into this Einstein's derivation. Einstein has a nice kind of popular book, which I think I forgot what it's called, The Meaning of Relativity, I think. And you'll find it there, only you have to adjust your notation to his bit old-fashioned notation. But it's quite readable. And yeah, and Feynman has given us his way of looking at it. There are many more things which unfortunately we didn't find time to discuss, particularly mass and energy. So maybe it might be better that next time we discuss mass and energy and momentum and twin paradox. I think that will complete the understanding of this subject at a decent level. Chapter 17, which is actually scheduled for my next meeting, is about geometry of space and time. But frankly, I feel that is very lovely stuff, but it is a bit advanced, and unless the basics are very clear, I don't think 17 will be very accessible. Again, I want to emphasize Feynman's lectures are very good to get a deeper understanding what we are doing. It's not always the way to get the first understanding. So if anyone is having difficulty with Feynman lectures, don't worry. I have difficulty with Feynman lectures. Everybody has difficulty with Feynman lectures. That is the whole point. He gave a very challenging and difficult set of lectures in order to illustrate the deeper way of thinking about these things. Okay.
Yes, sir.
Okay, there are no questions, then I can go ahead, I suppose. I feel that, so next time, if you don't mind, Dr. Vinod Kumar and Dr. Sumesh, can we continue with chapter 16, 15 and 16 only, instead of going to 17?
No problem, sir.
Because I think that maybe if there's time, I can make some statements about 17.
Sure,
but
sure.
It's more specialized, and it will be useful for people who really work in relativistic physics. While 15, 16, I feel these are basic requirements that every physicist needs to know.
Absolutely, sir.
Thank you so much.
Sir, I have a question to you as well as all of you. That could we extend this to Poincare transformation? Means if we have a discussion on Poincare transformations too, I think that would be much more concrete in the sense that this Poincare group is the Lorentz group is the subgroup of Poincare group. So if we have a total detailed discussion on that, I think that would be very helpful for all of us.
Thank you. You know, I at some suitable time, I don't mind discussing Poincare transformations, and from mathematical point of view, they are very useful and deep. But you know, I feel that goes very much in a different direction from Feynman lectures, which after all is what we are trying to discuss, because um, that comes in if you really want to understand quantum fields and all that. But here we are really talking about giving students, your students, a good sense of what is going on in the change of coordinates and physical quantities between two frames. And I want to emphasize, again, it should be in your minds also, that today I didn't discuss anything about mass, energy, and momentum. Okay, so we haven't discussed any physics. You might say that in a way, today the entire discussion, though it is framed in language of physics, it is only about kinematics. Okay, and if we bring in Poincare transformations, we will be doing more kinematics. But physics really is dynamics. It is the study of particles and objects, solid objects that interact with each other, that collide, that scatter, and we haven't discussed a single thing about that. So I think priority-wise, that's absolutely the highest priority. After all, Feynman also gives you an equation about mass.
Yes, sir.
And we haven't discussed that. And there's a mass energy equivalence, which is E equals mc squared, and we haven't discussed it. So in the limited time that I can contribute, I think we must discuss dynamics. So next time would be relativist. Today was relativistic kinematics. And is this recorded and the participants can watch it
Yes.
if they want? Okay,
Recorded, sir.
I'm happy. They are most welcome to watch. People can email me anytime. This is my email address. I'll just write it for you here. Oops. Not difficult to remember.
No, we'll share in the group also, sir. No problem.
Okay. Anyway, it's this at Gmail. So if you know my name, then you know my address. I was lucky to get it very early in life before other people were trying to grab all the Gmail accounts. So I don't need any numbers and all in my address. But in fact, when I got this account at that time, Gmail accounts were only by invitation. You had to get from someone who already has a Gmail account. Life has changed since then. Thank you all. It has been really a pleasure. But I do urge all the participants. I'm seeing a lot of names: Bhautik, Devbrat, Dinesh, Divyesh, Harshad, Krishna, Kranti, Tanveer, Naveen, Niraliben, Priyanka, Puneet, Sahaj Kumar, Suresh, Tapo we heard from a few times. Tejas, Trupti, Sagar, and another Priyanka maybe. Yeah, another Priyanka. I would really request you that please, and there are 6 more names here again: Ajay, Bhavin, Manish, Smriti, Kaushal, Dhruvid. Please make yourselves visible and please interact. And don't be embarrassed if you ask a very simple question. That is the only way that we all can learn. So next time, I'm seriously expecting that all these names will become actual familiar names to me.
Yes.
Thank you. Okay.
Thank you, sir.
Bye-bye.
Sure, sir.
Bye.
So
Thank you, sir.
Thank you, sir. Your time is you have to leave. So thank you very much, sir.
Yeah, I'm saying I'm thanking Professor Mukhi for a very nice interaction with all the participants. I hope all of them must have enjoyed this interaction.
I think he left, it seems.
I think he left, I think.